All right, let's start here. All right, scholars, so welcome. I have that it is that time. Let me see. No real announcements. I think we're just kind of progressing. So we're going to work on section 3.6 today, and I think we're on spring break next week, right? So pretty sure many of you have already begun, you know. I know if I was in a remote class like this, I would have already started by spring break, but I would still log in to get my credit and just still be present for it's only like an hour and some change. But yeah, but I would have either been on the road or something. Let me see. Are there any questions before we kind of get started? Any questions about anything going once, going twice? Okay, let's do like this. And I'll leave my notification on until it here until it gets distracting. Okay, we're gonna go like that. I think we're good there, so I'm not gonna worry about that for right now. Yeah, let's just kind of get into it. This section seems fairly short, so we'll get through the presentation as best we can, and then maybe we'll work on some questions from the homework to kind of close it out. So we're continuing chapter 3. We're actually almost done with chapter 3. I know we're going on spring break again next week, and then when we come back, we have a few more sections in this chapter, and then we're on to the final chapter. All right. So remember our goal, and we're pretty much matching the schedule that we have as outlined in the syllabus. So we've been doing pretty good about matching that. Let's see. Okay. Yeah. So anyway, let's move on. So let's see. Today we're gonna be working on section 3.6, marginals, differentials, and linearization. Get the student. Let's go like this. I think we're good as far as all this. I'm not gonna stress about it. A few objectives here. One, find the marginal cost. Find marginal cost, revenue, and profit. 2, find the delta y and dy, so the change in y and the differential of y. Use differentials for approximations and find the linearization of a function at x equals a. Let's see this. So we have a few definitions. Let C of x, R of x, and P of x represent respectively the total cost, revenue, and profit from the production and sale of x items. All right. So the cost function, revenue function, and profit function. Okay. The marginal cost at x given by C prime is the approximate cost of the x minus first item. Okay. So then the cost to produce like the 27th item or something like that, like one before the 27th item. So the marginal cost is going to be what? C of x plus 1 is approximately C of x plus 1 minus C of x. And then if we were to solve for C of x plus 1, we would get that's approximately equal to C of x plus C prime of x. Okay, let's see. So the marginal cost is our C prime, okay? So then the cost of producing our x plus first item, like say we've developed a cost function for producing 28 items. We want to say, well, how much will it cost to produce the next item, all right? And it's based on this information given here. So we have the cost function plus the marginal cost. And again, that's going to tell us about the cost to produce the next item, all right? That's essentially what it's telling us. Okay. The marginal revenue given by R prime is the approximate revenue from the X plus first item. All right. So the money generated by the production and sale of whatever the next item is. All right. Say we've produced and sold 30 items. We want to know how much money are we going to generate on the production and sale of the 31st item, the next item. Right. So all of these marginal costs, revenue, and profit, it's telling us about how much it costs to produce or the money generated or the profit from the next item. This is all about the next item in production. Okay, let's look at this example. So given this cost function and this revenue function, find each of the following: the total profit P of x, okay, the total cost, revenue, and profit from the production and sale of 50 units of the product, okay, and then the marginal cost, right? Is that our C prime? Let me see something. No, I want to see that. calculate something real quick. Okay, let's just see how it unfolds. I do need some space. What slide is this? This is slide 7. Let's copy and paste. Okay. And I need a copy of these guys. I think I can screenshot these. Maybe I can just take the whole slide because I kind of need all of this information. So I'm going to use this as a reference. So that's about the size I was anticipating. Why is it behaving like that? Okay. All right, so I'm just going to use it as a reference. I think I'll move it over here. Okay, and I need this guy. So the profit function, all right, that's going to be our revenue minus cost. So for part A, total profit should be the revenue minus the cost. Okay. So then that's going to be our x cubed minus 12x squared plus 40x plus 10. And then we need to distribute a negative into the cost function. So minus 62x squared minus 27,500. Okay. So then if we simplify this guy, we get what, x cubed, 62, 72, 74. So a negative 74x squared plus 40x. What is that, 490? Negative 490. So negative 27,490. Okay. So for part A, we got this is our profit function. So if we produce and sell X items, the profit generated is going to be given by this. So now we want to know the total cost, revenue, and profit from the production and sale of 50 units. All right. So say we produce and sell 50 units. How much is that going to cost? What's going to be the revenue generated, and what's going to be our profit? Okay. I think I'm just going to use my calculator there. Okay, let's go like this. Let's go here. Okay, so I'll put my cost function in Y1. That's let me try to type. So 62x squared, let me see, 62x is like this, x hat, where's squared? I think that's I, okay. 62x squared plus 27,500, 27,500, okay. And then we'll put our revenue function in R2. So this one, x at 3, withdraw 12x squared. So 12x squared plus 40x plus 10. Okay. All right. Let's go like this. So we want to calculate cost, revenue, and profit from the production and sale of 50 units. So I'm going to call on our cost function. We're going to let x be 50. We get this result. I'm going to call on my revenue function. So that's going to be the one that's in slot 2 or Y2. Production of so if we sell 50 units, the money generated should be this. Ooh, looks like we're in the red. Wait a minute. Yeah, that's what it looks like. Man, it looks like we are in the hole. So then the profit, if we said that 182,500 minus that 97,000, and that should be the profit. Maybe we're good. Cost? No, sorry, I got it backwards. It should be negative of that result, right? Because we got to see revenue minus cost. So that result is actually negative. Okay. So I'll just take my notes here. So then the cost to produce and sell 50 items, we basically just plug 50 into the cost function, and we got 182,500. Yeah, I think so. Okay. I got that the revenue generated from the production and if we produce and sell 50 items, the money generated is 97,000. Okay. And then the profit, if we say the revenue minus the cost, we're getting a negative. We're in the hole. 85,490. Okay. So I'm just going to kind of highlight all of this like that. Let me see. The marginal cost, revenue, and profit 150. So on the previous slide, so I think there are like two ways to look at it. Let me see. Let's see. There's that sound. Let's go like this. Turn it off. Because it was saying that the marginal whatever is like the derivative, right? But then this other one is an approximation. If we say p of x plus 1 minus p of x, so I'm not sure if they want to. I think let's just do the derivative, because there's two different ways we can express it. But again, the other one is an approximation. So let's first I'm gonna shrink this down just a little bit.
I have a question.
Yes.
So how did you get 50 to plug into the equation?
The 50?
Yes.
It was given right here. It said in part B, they want us to find the total cost revenue and profit
Okay. I
from
didn't
the
see
production
that.
and sale of 50 units right here.
Okay.
No worries.
It was kind of choppy. I didn't really see it.
It's okay. So I'm going to do this just by finding the derivative of each one. So for part C, let me see our revenue function. So R prime, we're getting 3x squared minus 24x plus 40. Okay. Our marginal cost function, what is that? 124x. I think that's it. And then our marginal profit function. I guess we could just do the revenue minus the cost. I don't see why that wouldn't work. Let me see. If I took this derivative, 3x squared, let me see, 148, maybe not. It might work. X, no, well, they're different. So I'm going to take the derivative of our profit function. So it looks like we're getting 3x squared. I feel like I kind of want to look at it, but I'm just going to go ahead and finish this. And then if we're doing it wrong, we'll fix it. Let's see, 140, 148. I'm just going to glance at it. Let me see. I think these are good, right? I think we got that for our profit, minus 74. That looks okay. 182, 97, and negative 85 for 90. And then our marginal, C prime. Okay. Yeah, I think what we're doing is fine. Okay, that's fine. Okay. So then we want the marginal revenue from the production and sale of 50. So we would say R prime of 50. So we're going to plug 50 into that. C prime of 50 and P prime of 50. Okay. Now I think we can. Let me see if I can remember how to do this. We can actually. I think this will calculate the derivative. Let me see. If I go to, was it math? No, let's go to let's try stat. Calculate. No, it's not that one. It's not that. Move, stat, variables, distribution, draw. Where is it? Not that. It's not, let me see. No, stat. Let me, I forget where it is. It's not that. Let me try this again. Number. It's none of those. It's not that. Where? It's not that one. Stat plot format calculate. I don't think this was it. No, you. Maybe this could work. dy by dx. No, I think it's gonna force it to the graph. Hang on, just give me a moment. If I go to variables, no. I don't think that's it either. List. Let me try list. Math. Standard deviation, variance. That's good to know. Those are there. I did this like the other day. Where is it? What am I missing? Math, programming. I might have to let it go. Let me check this one more time because I thought it was something different. I remember clicking something different. I just don't remember what I clicked. And I'm not seeing it in any of the options. I don't think it's those. Okay, there it is. Okay, so it wasn't math. I just didn't look properly. So if we go to number 8, right? We want to take the derivative. Let me see. Function. I think it was like y1. This is our what? Our cost function. With respect to x. I'm trying to think. When x is 50. Oh, that's our revenue function. Let's see if this works. 62. Let me see. Okay, I think this may have worked. Let's see. So if we say 3 parentheses 50 squared minus 24 times 50 plus 40. Okay, let's see. Cost. Okay. So this was our cost function. Okay. Let's try this one more time. So right here, 124 times 50. Yeah. So y1 was our cost function. So it does work. Okay. So our cost, it's just, I think the way I wrote it was different than the way I put it in the calculator, so it's doing me for a loop, right? So when we plug 50 into C prime, we get 6,200. Oops. Okay. So then I guess we can just go math number 8. And then we want to call on the second function, which is our revenue function. We want to take the derivative with respect to x and evaluate it when x is 50. And that one is 6340. And then we have our profit function. So we can plug in 50 into the profit function. Let me see. 140. Let's see if that works. So we're going to say 3 times 50 squared minus 148 times 50 plus 40. Okay, I think that's what we said, right? 140. So we could have also just done the revenue minus the cost, and we still get the 140. So that's reassuring. Okay. So the marginal, so I think what it's saying is that if we produce and sell the next item, the revenue generated from the sale of the 51st item should be 6340. Let me see. Let me look at it here. Okay, so we got A and B, and then so when 50 units have been made, the approximate cost of the 51st item will be 6,200, right? So the marginal cost, marginal revenue, and the marginal profit tells us about the next item, right? The marginal cost, like if we have the marginal cost of 50, that's telling us information like the cost to produce on the 51st item, how much it was going to cost to produce that item. The marginal revenue of 50 items is telling us that it's going to cost 6,340 to produce. We're going to generate 6,340 on the 51st item, right? And then the approximate profit on the 51st item is going to be $140. Okay, so these marginals tell us about the next item. That's essentially what it's telling us. Gives us information about the next item. Okay, so for this y and this x and this change in x, find the change in y. Okay, so the change in y, let me see. Okay, I'm going to kind of do this from scratch. So it's like this. It might not match what they have, but let me see. Do we know the slope? Okay, so I'm kind of piggybacking off the slope formula, right? Like the slope is what the change in y over the change in x, right? And we said the slope is the derivative. So if we wanted to change in y, I think we can do like delta x times the slope, right? And the slope looks like it'll come from the derivative. Okay. So I'm just gonna piggyback on the slope formula and then see if we can get all the parts. Okay. So let's find our dy by dx, our derivative. It's gonna be 2x. And normally I don't think we need the dx just yet. But we get 2x, right? So then, and they gave us delta x. So then now if we solve for delta y, right? It's looking like delta y is going to be this 2x times delta x. The delta of the triangle just means a change, some change in the x value. So we want to find the corresponding change in the y value, right? Now they gave us information here. Let me work up here. So then delta y is going to be 2 times, now x, it says that x is 4, and delta x is 0.1. So I guess 0.8. And again, I kind of did that based on the slope formula, slope being the change of y over the change in x. Also with slope being the derivative, right? I just basically took the derivative. Let's see, how do we do? So let's look at the prepared notes. Close. So let's see. Change in y. Okay, so f of x2 minus f of x1. Okay. I think I may have found like the differential. Okay, so let me kind of strike through this. This is close, and I think this comes into play, but we're going to kind of put a pin in it for now. So the change in y is basically, like, you can look at it as f of x2 minus f of x1, right? Let's see. Okay. So then if the change in x is 0.1, then that means we're going to be evaluating f of 4.1. I just said the x plus the change in x. So f of 4.1 minus f of 4, right? And then that's all that we're doing. And then, let me see if I can just do it quick here. Here it is. So let me see. We said 4.1 squared minus 16. So 0.81. Okay, that's fine. I still feel like the way we did it before. It's so the thing at play here, you have what we're kind of like exploring is the change in y versus the differential. The change in y is like the literal, like if you have 2 points, what's the difference in your y values? The differential in y is like, okay, if you have a point on a curve, you consider the tangent line at that point, and then that tangent line is going to have a slope, and so the y component of that slope is the differential. And so the differential is oftentimes close, but not necessarily. It's approximately equal to the literal change in y. So that's actually what we experienced here. They wanted the actual change in y, so we had to say y2 minus y1. I think what we found initially was the differential. Remember, we took the derivative and we did it based on the slope, and that's why they're close, but not equal, right? I could draw a picture, but I feel like it would make it worse. But again, let me just do a quick recap on that. The change in y is the literal like difference in your y value. So it's like y2 minus y1. I think what we found was the differential. It comes out of like if we had that point, the first point, and we consider the slope of the tangent line. When we're evaluating that slope is what? The change in y over change in x, and it's going to be an approximation, right? So that's why they're close. So we did ours based on the tangent line versus the actual point, and that's why they were close but not exact. Okay. So I know that's a little bit circular, but that's what it was. And again, I could draw a picture, but I don't. I'm just trying to avoid that because I feel like it might make it worse. Okay, so we're gonna let that be. I usually leave that as an exercise, and I think this is getting into what we just did. So differentials and delta notation for a function f, a continuous differentiable function, and some small change in x. So f prime, which is the slope of the tangent line, is going to be the change in y over the change in x. And so therefore, and this is what we literally did in the previous one. This is the technique. That's why I was like, which one are we using? But So then delta y is approximately equal to f prime times delta x, which is what we experienced, right? We did it both ways in the previous example, right? So the change in y is approximately equal to f prime times delta x. Okay. All right, let me see if I can remember this one. So we're asked to approximate this using that the change in y equals f prime times delta x. Let me think about it. Okay. So give me a moment. Okay, so I know this comes out of like we're using this concept where the square root of 27 is actually close to a perfect square, but it's not a perfect square itself, right? So we can use a close result to get an approximation of this guy, right? So let me think. Okay, so the square root of 27 should be close to. We can use the square root of 25. Let me see. Plus some change in y. Right? Plus some change. Let me think. Are we using the square root of x? Or what would be our function? The square root of x? So if we let f be the square root of x, let's see if that works. Let's just try it. So if we let f be the square root of x, right? So then f prime, this is getting funky, 1/2 x to the negative 1/2. Okay. Now, what's our change in x? It looks like our change in x is 2, right? Because we're basing this on the square root of 25, but we want the square root of 27. So the change in x is going to be 2, right? Okay, let's see if we can, let's keep going with this train of thought and see what happens. So then we'll get 5 plus, now f prime, 1/2 x to the negative 1/2. We're going to come back to that. Times our delta x. our change in x looks like it's a 2. Okay. And I think our x in this case is 25. Right? We're starting with where x is 25. I think this is okay. Let's keep going. Let's see what happens. So we get this 5 plus, now if we got 1/2, we got 25 to the power of a negative 1/2 times 2. Let's crunch that number and see what happens. So the square root of 25 is 5, so that's a 1/10. So now it's looking, we have a 5 plus 2/10, or I guess the 2's will cancel out. It looks like this guy cancels this guy. Right? So then we just have 1/5. Which is that what, like 5.2? Maybe. Let's see why not. So when we did it, we got this, right? Let me check and see if this is correct, and then we can kind of go back and like analyze it a little further and like break it down. Okay, and that kind of makes sense, right? Because the square root of 27 is slightly more than the square root of 25. So then you would expect that square root to be slightly more than 5. Let's see. Okay. So let f of x be the square root of x, and x equals a number close to 27, and a number for which the square root is easy to compute. So we're going to let x be 25, and the change in x is 2. Bing, 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 right? 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 That's exactly what we did. So then f prime, we got that, we got that. I think we got the 0.2. Yeah, I think we got that. Yep. That's exactly what we got. Okay. Yeah, so we got the change in y. Yeah, so we got the change in y to be 0.2. So then we said that 27 was approximately the square root of 25 plus some change in y. Now we kind of built it a little bit differently, but we did the same thing, right? That was trippy, all right? Because we actually started here. Square root of 27, we knew that that was close to the square root of 25 plus some change in y, right? Because we're talking about y values at this point. So then we went back and built this guy, and we got that result. So then I think we got that result there. That's so interesting. Wow. All right. Okay. Okay. We're going to leave this as an exercise. Let's look here. So we got another definition. Actually, let me check in you guys in Zoom. I know I would see this is like when I have people start to come and go, that gets distracting to me. So I turn off the sound effect, and then I forget to check at the 15-minute mark. Hopefully, there's nobody in the waiting room, so I think we're okay. Hopefully, we didn't miss anybody. Let me see. So for y equals f of x, we define d of x, called the differential of x, and we're going to define it by the differential is going to be equal to the change in x. So our dx is equal to delta x, but dy is approximately equal to delta y. All right. Let me say that one more time. For all intents and purposes, dx is equal to delta x. These two guys are equal, but our differential dy is going to be approximately equal to our change in y. It's not gonna, it doesn't carry like this guy is. But this one, it can be equal. This guy is close to delta y, right? So we call dy the differential y is given by f prime of x dx. Okay. Okay. So for this function, find dy, and then find dy when this is our x and this is our dy. Okay. So on the previous slide, we just said something to the effect of, so our differential of y is going to be f prime of x dx. Is that equal? So we're going to kind of do that. Okay. So then for part A, okay, so I'm going to do this one a little bit differently than the way we've done it. When we start working with differentials and stuff like this, like isolating the dy. So what I'm going to do here, whenever I take the derivative of x, I'm going to put dx next to it. All right. Yeah, whenever I take the derivative of something, I'm going to put dx. Like if I take a derivative with respect to x, I'm going to put dx, right? And that's a good habit to kind of start to build because it does come into play like in a few of the later concepts. So we'll just kind of introduce it here. Okay. So now normally what we do is say dy by dx, but here, if I'm going to take the derivative, my differential of y. Now, when we're working on the right-hand side, I'm intentionally not writing it as dy by dx. You could, and you can kind of argue like doing algebra to get that to work as well. But I just want you to see the technique. Let's see. So now on the right-hand side, we have what? X times this 4 minus x quantity cubed. So it looks like we need to apply the product rule, right? First times the derivative of the second plus the second times the derivative of the first. So if we say the first, which is going to be this guy, the derivative of the second is going to be what? We got a 3. We got this 4 minus x squared. And then times the derivative of the inside is going to be what? A negative 1. And then because we took the derivative with respect to x, we're going to put a dx here. And you can kind of treat it like algebra for now, and I think it's okay. So we said the first times the derivative of the second. Now we're going to say plus the second times the derivative of the first. So the derivative of x is a 1, but because we took the derivative, again, we're going to put dx. Okay. All right. So I think both of these terms, so I think we have common things that we can factor out of both terms. Okay. So then our dy. Now what's common to both? All right. Let's go here. It looks like they both have this dx. They both have at least 2 of these guys. All right, they have at least 2. And I think that's it, right? So that's what we're going to factor out of both. So we can factor out a 4. We can factor out 4 minus x squared. The dx I really wanted to be on the end. I wanted to be over here. I'm going to move it around a little bit momentarily. Okay, so then what's left? The first term, it looks like what's left is going to be negative 3x. In the second term, it looks like we still have an additional 4 minus x, right? So we can say plus 4 minus x. And then now we put the dx on the end, right? So I factored out my dx, I factored out my 4 minus x squared, and then I grouped whatever was left over. And then just one more step to kind of combine like terms. So our dy is going to be 4 minus x squared. That's going to be a negative 4. So I'm going to write that as 4 minus 4x dx. Right? You could have also, another way you could have done this, in the beginning, just write dy by dx, then do your product rule, and then use algebra to move the dx to the other side. That would be okay here as well. But I just wanted to kind of showcase, when you take a derivative, include the dx. When you take the derivative, include the dx, right? So when our dy, our differential of y, we got this guy. Okay. 4 minus x squared. Okay, so they factored out the negative 4. That's fine. And that would be x minus 1. That's fine. Dx. Yeah. And so I think they did the second way I suggested. They just went on and did dy by dx. They did their product rule. And then at the end, they multiplied both sides by dx to move the dx to the other side. That probably would have been a little bit easier. Sometimes, you know, appending that dx like I did was easier. And sometimes doing it this way is easier. It's just, you kind of have to take it case by case. Okay, this is part B. Oh, forgot about part B. Find the differential of y when x is 5 and dx is 2. So you just plug those in. Let me see. That's going to be a 1. 4 minus what? 20 is negative 16. Negative 3.2. I'm just going to put the result. I got to be up. For B, I got a negative 3.2. When you plug those in, if you let x be 5 and dx be 0.2, I think I got negative 16 times 0.2. I think that's okay. Mm-hmm. Okay. All right. Okay. I wasn't going to draw this image, but I feel like it might help. So say this was our positive x and this was our positive y, and we were considering some curve, right? And here's our original point. Delta y, like, and if we consider some second point, that's going to be the actual change in our y values, right? So if this is our y2, this is our y1, delta y would just be y2 minus y1, right? But our dy, our differential of y, comes from, if we consider the slope of the tangent line at the point, something like that. And then we consider this point here. So then, right? This guy here is our dy. Right? And so notice here that our dx is equal to, here's our x1, here's our x2, is equal to our delta x, right? So the change in x is equal to dx, but dy is close to delta y, right? And delta y is basically this part. Right? Or let's do it this way. Delta y runs from here to here. So this is the image that I was kind of like referencing in my mind. I'm kind of talking about this stuff. Right, the dy is the y component of the slope of the tangent line. The delta y is the literal y2 minus y1, or your change in y. Okay, so this is the image that I was like avoiding, but that's what it is. Okay. All right, so what the linearization is, so this is the final topic for today. Linearization is basically a way for us, like, to jump straight to the equation of the tangent line at a point, right? So if we have a curve, we consider a point on the curve, then we consider the tangent line at that point on the curve. Normally, we just kind of talk about the slope of the tangent, but what if we want the equation of that line itself, right? So that's what the linearization does. It's a way for us to, jump straight to the equation of the tangent line at a point. The derivative tells us about the slope, but the linearization will take us straight to the equation of the tangent line at the point, right? So given a function, let y be f of x, let y equal to f of x be differentiable at x equals a. The linearization of f at x equal to a is given by, we're going to have f of a plus f prime of a times x minus a. Let me see. This is like the point slope formula, right? So from college algebra 1, point slope is what? Y minus y1 equals m times x minus x1, right? And let me see. Right? And so, and say the point that we're considering is when x is a and then the corresponding y value, right? So then if we plug that in, we're going to have y minus f of a. The slope is going to come from f prime of a, x minus a. And then, so then once you solve for y, you get this guy here, right? So that looks like that comes out of the point slope formula, given a point and a slope, right? Which we have. If we have a curve, we have a point on the curve, and then we take the derivative, that'll give us the slope. So then we can use point slope formula to get this guy. That's interesting. So this is the equation of the tangent line to f at x equals a, right? So this is a way for us to jump straight to the equation of a tangent line at a point on the curve, right? So find the linearization of this guy when A is 27 and use it to approximate, okay, the cube root of 27. Okay. All right, so on the previous slide, we just said y equals, let me see, I know we had f prime of A times x minus A plus f of A. Okay. Okay, so we're going to use that. And again, that comes out of point slope formula. And we just kind of switched out that point for A comma FA. All right, so let's find all the components. Let's start off with F. Let's start off with, well, we're given f of x. I'll just write a copy of it, cube root of x, okay? Let's go ahead and find f prime of x. So the 1/3 comes down, x to the negative 2/3, okay? Okay. Let's see, let's look at f of a. Now our a is 27, so let's look at f of 27. So that's going to be the cube root of 27, which is what, 3? Okay. Let's look at f prime of 27. I'm just doing all the components separately, then I'm going to put them all together in the formula. So if we plug this into f prime, let me see, cube root of 27 is 3, then that's going to be a 9. 9 times 3, so that's going to be 1 over 27. Okay. Okay. All right. So then the equation of our line, we're going to have y equals f prime of a. So we got 1 over 27. Our a is 27. And our f of a looks like it's a 3. Okay. So then we can simplify this guy. 1 over 27x. Let me see, what is that? Minus 1 plus 3. So it looks like it's plus 2. So this should be the equation of the tangent line when x is 27 for the cube root function. Okay. Give me a moment. I'm just trying to see how, trying to think how to like tie that into the cube root of 28. Let me see what we had on the previous slide. Okay, so y equals f of x. So then, okay, so if we let x be 28, okay. So now we got this result for the equation of the tangent line. Let me see, is it equal or approximately equal to? So this is equal. So then if we want to evaluate the cube root of 28, so that basically means let x be 28. It should be 28 over 27 plus 2. Siri, what's 28 divided by 27 plus 2?
28 divided by 27 plus 2 is approximately 3.037.
So slightly more than 3. That makes sense. Siri, repeat that answer.
28 divided by 27 plus 2 is approximately 3.037.
Okay. Okay. Let's see. All right. So to construct a linearization, we need to find both f of a and f prime of a. So here a is 27. So let me see. F of a, we got 3. F prime of a, we got both of those results, 1 over 27. So then the linearization of f at 27 is going to be the equation of the tangent line when x is 27. X over 27 plus 2. X over 27 plus 2. Come on. Okay. So then the cube root of 28 is approximately, I think this is exactly what we got. Okay, so that's repeating. I didn't realize I was repeating. So we can capture that like this, and I'll just do it in another color, right? Basically, 037 is repeating. Okay, let's remove it because of the way I think the way we calculated it, I don't think we necessarily got that result. But you know, again, these are all approximations, so this is going to give us something that's close, right? Just trying to make a distinction between this and that. But yeah. Let me see. Right, that over times 2, 54. 54 plus 28. So 84 or 82? 82 is fine. Okay. So if we use the linearization, we'll get something like this, right? Because I think we got this. But then if we just in the calculator put the cube root of 28, we get this. And again, notice that they're close, right? These are approximations. So, okay, not bad. Okay, so we have a solid 20 minutes. We'll probably hang out for another 10 minutes and then we'll call it a day. Maybe a little bit more than 10 minutes. Come on. So let me see. Let me copy. Why is that not showing up? Okay, that's weird. Okay. So I think what I'm gonna do, let's work a few questions from the homework. Matter of fact, let's just work here. Full screen. Let's go here. This one. No. This one. Let's go here. Let's go to section 3.6. Marginals. Yes, this is what we're working on today. Hey Google, give me a random number between 1 and 25.
22.
All right, let's look at this. Let's see if I can zoom in just a little bit. Yeah, I think that's about the best we can do. All right, it says businesses and individuals are frequently concerned about their marginal tax rate or rate at which the next dollar earned is taxed. In progressive taxation, the 80,000 first dollar earned is taxed at a higher rate than the 25,000 first dollar earned at a lower rate than 140,000 first dollar earned. That's so weird. Use the graph showing the marginal tax rate for 2014 to answer the following questions. Was the taxation in 2014 progressive? Why or why not? Let me see. So, showing to the right marginal tax. Let me see. Let's back up. The next dollar earned is taxed at a higher rate than the next one from there, and at a lower rate than. Okay, so it's higher than that one, but lower than that one. Let me see. 80,000. 40%. So 80. Okay. Is higher than the 25,000. Let me see if that's 100. If that's 50, 80 is about there. Okay, that's 89. Okay. The 25th is there. Okay, but lower than that. Okay. Use the graph shown on the right to answer the question. What was the taxation? Was it progressive or not? Let me see. It looks like it would be a yes. Let me see. In progressive taxation, that dollar is higher than the 25th, but lower than the 140th? Yeah, and it is, right? It's kind of hard for me to, because I don't have my cursor. But like for instance, this one is 89,000. That's higher. That rate is like 28%. It's higher than the previous, which is like 25%, and lower than the next one. So to me, that indicates a progression. Let me see. No. Let me see. I feel like it's not the first one and not the last one, because I feel like it is progressive. Right. So I would rule out the first one and the last one, because those are saying that it's not progressive. Then if we look at the second one, it's saying that it was progressive because the 80,000 first dollar earned is at a lower rate. Nope, that's backwards. So I think it's C, right, through process of elimination. In 2014, the taxation was progressive because the 80,000 first is higher than the 25,000 first dollar earned and lower, right? It matches, right? So I'm just gonna go with C. I'm just matching what it said. That was it? Okay. We got time for one more. Hey, Google, give me a random number between 1 and 25.
11.
Okay, let's look at 11. So for this function, for this y, this x, and this delta x, find the change in y, okay? So the change in y was what we said when we did it a moment ago. It was y2 minus y1, all right? So y2 is going to be found by saying x plus delta x. So that's going to be 4. If we plug 4 in, it looks like we get 11, right? So if we say y2 minus y1, y2 looks like it's 11. Right here. Oh, we got to go like this, off. Okay. Okay, so we're going to say 11. More. Oh, here, let's go like this. So y2, we got 11 minus, now y1, we just plug in x. That's going to be 6 minus 1 is a 5. So 11 minus 5 is going to be 6. So the change in y, we just said y2 minus y1. Now for the second part, to find our dy, we're going to say f prime times dx. And remember, we said that dx is equal to delta x. So we need to find, let me see, f prime looks like it's just going to be 3. And dx is 2. So then 3 times 2 gives us 6. So our dy looks like it's, wait a minute. They want f prime. F prime looks like it's just 3. So I'm going to just put 3 there. Okay. So then the dy, again, it's just going to be 3 times dx. Dx is going to be equal to delta x, so 3 times 2 is going to be 6. And I think we're out. Okay. All right, gentlemen, I need to get ready for my next group. Are there any burning questions before we go our separate ways? Let me go ahead and make a copy of, not having to write anything. Let me share. I'd like to send it to Box. Come on. Trying to let my people go. Let me back up here. Spring, traditional, come on. Calculus, notes, come on. Updated daily. This should be, yes, that's correct. I still need to change that one, but I'll fix it later. Send it there. So when this bar finishes loading, you'll receive a copy of the notes that we took today. Let me just check on you guys' Zoom real quick. Let me get the students. Tatum. Right here. Okay. So no real announcements. Like you know, we just kind of wrapped up section 3.6. I think next week we're off for spring break, so then we'll be off for that week, and then the week after that we'll resume our regular schedule. If there aren't any burning questions, we're going to go ahead and end the session here. And from one beautiful mind to another, Enjoy your evening, enjoy your spring break, and let's come back ready to finish strong. Take care. Peace.